For a really long time, researchers have persuaded us that the universe is continually growing. This conviction has intrigued researchers and scholars who have adopted the Big Bang theory as the most generally accepted explanation for the origin and development of the universe. According to this hypothesis, the universe began in a very dense and hot state and has since undergone persistent growth. However, the James Webb Space Telescope has made an astonishing revelation that challenges this hypothesis. How did the Space Telescope challenge the idea of a growing universe, and what does this mean for our understanding of space? Join us as we explore the new, stunning discovery from the incredible James Webb Telescope. If you're keen on staying up to date with news from the universe and its surroundings, subscribe to our channel, like this video, and turn on the notification bell. Albert Einstein's general theory of relativity provides a framework for understanding how the presence of heavy objects curves spacetime. According to this hypothesis, the universe began as a singularity, a point of density and temperature around 13.8 billion years ago. As indicated by the Big Bang theory, all matter and energy were compacted into a tiny, hot region. At that moment, the universe began to grow with a rapid and violent event known as the Big Bang. During the first few moments following the Big Bang, the singularity experienced a massive release of energy. The universe was filled with an incredibly hot, dense, and energetic plasma containing protons, neutrons, electrons, and their antiparticles. As the universe cooled due to its expansion, the temperature decreased enough to allow electrons to bond with protons and form neutral atoms. This process, known as recombination, allowed protons to move freely through space, resulting in the cosmic microwave background radiation that we can detect today. The expansion of spacetime itself may represent the expansion of the universe. This expansion doesn't imply a growth through space where objects move away from a central point but an expansion of space itself. We can imagine it as the surface of an inflating balloon. The points on the surface move away from each other as the balloon inflates, not because the points are moving, but because the space between them is expanding. Similarly, in the case of the universe, galaxies and other celestial objects are pulled by the expansion of space rather than escaping it. So, what is the source of this expansion of spacetime? According to scientists, dark energy is a theoretical form of energy that is thought to permeate all space and apply negative pressure. This dark energy is believed to be the cause of the accelerating expansion of the universe. In recent years, observations have revealed a phenomenon crucial to understanding the significance of dark energy: the balance between gravitational forces and the expansion of the universe. Gravity, an attractive force acting on massive objects, tries to slow down the expansion of the universe. If the universe were made solely out of matter, such as galaxies and their corresponding mass, gravity would eventually halt the expansion and lead to a phenomenon known as the Big Crunch. However, observations reveal that the expansion of the universe is accelerating rather than slowing down. This implies the presence of a repulsive force that counteracts the effect of gravity. This repulsive force is generated by dark energy, which is evenly distributed in space and applies negative pressure. The exact nature of this energy remains one of the greatest mysteries in modern cosmology, and scientists are actively investigating its characteristics. Although dark energy is responsible for the accelerating expansion, the distribution of matter in the universe also plays a crucial role. The density of matter and energy influences the curvature of spacetime through the equations of general relativity. Regions with higher density exert a stronger gravitational pull, which slows down the expansion of the universe. Conversely, regions with lower density experience a weaker gravitational attraction and contribute to the overall expansion of the universe. Matter in the universe isn't evenly distributed, but is organized into massive cosmic structures such as galaxies, clusters, and superclusters, which are interconnected by vast cosmic web-like filaments. These structures form due to the gravitational collapse of regions with higher density under the influence of gravity. As the universe expands, these cosmic structures experience a stretching of spacetime. However, gravitational forces within these structures counteract the expansion to some degree, resulting in a complex interaction between the expansion of spacetime and the gravitational pull of mass. On larger scales, the expansion predominates, leading to a continuous stretching of the cosmic web. It's essential to note that the expansion of the universe doesn't imply that galaxies are moving continuously through space. In fact, galaxies may come closer together on shorter scales due to the influence of gravity. However, on a larger scale, the overall effect of the expansion is to increase the distances between galaxies over time. Various observations provide abundant evidence for the expansion of the universe. One significant example is the redshift of light emitted by distant galaxies. As the universe expands, the wavelengths of light from these galaxies are stretched, shifting towards the red end of the electromagnetic spectrum. This phenomenon, known as the cosmological redshift, provides undeniable evidence for the expansion of spacetime. Another critical piece of evidence is the cosmic microwave background radiation, CMB, which is a remnant of the hot early universe. The CMB shows a surprisingly uniform distribution of energy across the sky, with small fluctuations that reveal significant information about the initial conditions and subsequent evolution of the universe. Extensive CMB studies have confirmed predictions of an expanding universe and reinforced the Big Bang theory. Observational data from large-scale surveys like the Sloan Digital Sky Survey and the European Space Agency's Planck satellite mission have provided precise information about the expansion rates of the universe and the distribution of matter and energy within it. These discoveries have improved our understanding and contributed to the ongoing search for information about the fundamental nature of the universe. One of the most intriguing aspects of the James Webb Space Telescope's universe surveys is its ability to map the large-scale structure of the universe at high redshifts when galaxies were still young and grouped into massive clusters known as protoclusters. These protoclusters are the ancestors of today's galaxy clusters, which are the largest gravitational structures in the universe. By studying these protoclusters, we can learn about the interactions between galaxies, their interactions with their surroundings, their growth and mergers, and how they influence the formation of stars and planets. Protoclusters are extremely intriguing and difficult to find because of their wide spread across the sky and low surface brightness. However, the James Webb Space Telescope's wide-field and high-sensitivity cameras make it possible to identify many galaxies in a single observation, covering a large portion of the sky with unprecedented depth and detail that has never been seen before. Astronomers can identify protoclusters by analyzing galaxy density, spectral properties, and spatial distributions. To do this, they combine data from the James Webb Space Telescope with other observatory surveys. The James Webb also provides information on the masses, ages, star formation rates, dust content, and gas kinematics of individual galaxies within protoclusters. These observations will reveal the differences between galaxies within protoclusters and those in less dense environments, as well as their evolution over time within their host structures. Additionally, the James Webb will allow us to study the intergalactic medium, IGM, around protoclusters, which is enriched by supernovae and active galactic nuclei, AGN. The IGM regulates galaxy formation by supplying gas for star formation and ejecting it through winds and outflows. However, images captured by the James Webb Space Telescope are challenging the Big Bang theory as they show galaxies of immense sizes that appear not to have been able to exist or are inconsistent with the Big Bang theory. These candidate galaxies are estimated to have formed roughly 13.3 billion years ago, between 500 and 700 million years after the Big Bang. Astronomers had expected to observe young, small galaxies in this region of early space. However, images captured by the Space Telescope reveal that these stellar systems may contain about the same number of stars as our own Milky Way galaxy. Instead of finding small, young galaxies, this discovery shows mature galaxies like our own in what was thought to be the dawn of the universe. The James Webb Space Telescope is equipped with infrared sensors capable of detecting light emitted by older stars and galaxies. This allows astronomers to look back in time nearly 13.5 billion years to the beginning of the known universe. Before this discovery, scientists had identified numerous galaxies in the oldest regions of the universe around 350 million years after the Big Bang using data collected by the James Webb. These distant stellar systems were small and consistent with the predictions of current cosmological models. However, the current discovery of 6 mature, massive galaxies in the same region of the early universe raises the possibility of challenging current cosmological theory and altering what has long been considered accepted scientific knowledge. It is astonishing to think that the early universe may have organized itself so quickly since these galaxies didn't form at that time. These new discoveries emerged from studying a region near the constellation Ursa Major, first observed by the Hubble Space Telescope during the 1990s. The candidate galaxies are so striking that they contradict most current cosmological predictions. According to current measurements, there shouldn't be enough material to form large stellar systems 500 to 700 million years after the Big Bang. The researchers believe that to explain the observed mass of these galaxies, it would be necessary to either modify current cosmological models or revise our scientific understanding of how galaxies emerged in the early universe. Both theories require a fundamental change in our understanding of the early formation of galaxies in the universe. These unexpected objects have been humorously named universe breakers and have so far lived up to their name. Although more data are needed to confirm that these candidate galaxies are as large and old as they appear, the data suggests that they are likely to be real galaxies. There is the possibility that some of these objects are obscured by very massive black holes, which is another intriguing aspect to consider. However, the amount of mass found suggests that the known mass of stars at this stage of the universe is up to 10 times larger than previously thought. Although the sample is small, it is still a remarkable difference. It is possible that these objects are not galaxies at all. Another possibility is that there are other types of strange objects, such as faint quasars, which would be very interesting. Even if only one of these galaxies turned out to be real, it would have a significant impact on our understanding of the limits of our cosmological understanding. In the meantime, preliminary observations offer compelling insights into how the James Webb Telescope could ultimately change our understanding of the universe. The rapid pace of discoveries made by the James Webb is similar to the early days of the Hubble Space Telescope, which was launched into low Earth orbit in 1990. The Hubble Space Telescope quickly began to provide a much more complex picture of the early universe than experts had initially expected. Scientists have made another discovery that challenges the notion that the universe is expanding at the same rate in all directions. This finding casts doubt on the widely accepted theory that the expansion rate is uniform in all directions. A recent study based on data from the European Space Agency's XMM Newton survey, NASA's Chandra, and the German Rosat X-ray observatories revealed that this cosmological premise might be incorrect. A PhD researcher in astronomy and astrophysics at Bonn University, along with his supervisor, set out to investigate the theory of isotropy. According to this hypothesis, the universe has the same properties in all directions on large scales, with minor deviations generally accepted as a consequence of established fundamental physics. This premise has been supported by observations of the cosmic microwave background, CMB, which is a direct remnant of the Big Bang and reflects the universe in its early stages when it was only 380,000 years old. The uniform distribution of the CMB across the sky suggests that the universe expanded rapidly and uniformly in those early times. However, in the present universe, this might not be true. The researchers studied the behavior of more than 800 galaxy clusters in the present-day universe in collaboration with colleagues from the University of Bonn and Harvard University. If the isotropy hypothesis were correct, the clusters should have uniform properties across the sky. However, they observed significant differences. They compared data from X-ray temperature readings of the very hot gas found in the clusters with the brightness of the clusters in the sky. One would expect clusters with the same temperatures and the same distance to appear equally bright, but this is not what they found. They discovered that clusters with similar properties and temperatures appeared less bright than expected in one direction of the sky and brighter than expected in another direction. These differences were quite significant, showing around a 30% variation. Moreover, these variations were not random but followed a clear pattern depending on the direction in which you looked at the sky.